Welcome to the Minelab Manticore ID and target tracing tutorial. We're going to take a look at the multiple layers of information you have at a glance. On the top of your map, you have a target ID. It ranges from 0 to 99. Targets detected will have an ID of 1 for less conductive, ranging all the way to 99 for more conductive. Here, you will see how ferrous your target is being classified. The further from the center line, the more ferrous the target is being classified. This is your ID map section. Within this, you will see your ferrous limits, upper and lower ferrous limits. This controls what targets will be classified as ferrous. Here, you have your target tracing. When you detect a target, you will see a black dot or smudge. The opacity of the dot actually determines the signal strength. The darker the dot is, the stronger the signal strength is. You will also see your discrimination pattern. You will notice a change when using a single frequency versus multi to your ID map. When using a single frequency, there is not enough information to plot the conductive and the ferrous properties. Therefore, the map was simplified. The ferrous limits is disabled. Non-ferrous targets will only appear on the center line, and the ferrous will be lower to the left. In single frequency, the target ID range will be 0 to 99 for non-ferrous, and 1 to 19 for ferrous, with a red ferrous indicator. Target trace. Target trace is a feature that's worth taking the time to learn. Most targets will give you a distinctive trace. The target trace will fade after 5 seconds, just like the target ID does after you detect a target. One characteristic that you will notice is that some trace may appear weaker and more transparent. Others will be dark and solid. This is telling you a lot about the signal strength. Strong targets will appear much darker. The trace gives you more information than you get with audio alone. The factors that can affect the target trace shape, along with where it falls on the target ID map, are metallic compositions, complexity, orientation, depth, swing rate, and the frequency settings. Non-ferrous coins will show up as a black dot on the center line. Less conductive coins, like cut or hammered coins, will show up more to the left. High conductive coins, such as a large silver, will show up more to the right. Those countries who use ferrous coins, these will not appear on the center line. More complex targets that have ferrous and non-ferrous properties, such as bottle caps, will appear further from the center line, but orientation will affect its target trace. There are chunk targets that can appear on the center line. Example is an aluminum pull tab. They look similar to a coin with a distinctive round dot. I did notice in many cases my dot was slightly elongated at times, allowing me to identify them. I dug them out anyway, as there's always a small chance of gold reacting similar, or you can just use your discrimination pattern to no longer hear them. Doing this, you may still miss targets that share the same target ID, but it's a great option to use when you want to focus on more desirable finds. Ground noise target trace. Ground noise is caused by hot or mineralized ground that contains a lot of iron. This is a good indication that you may need a ground balance or reduce your sensitivity to deal with your ground conditions. How orientation will affect your target trace. As an example, we're using a bottle cap. Here is a common beer bottle cap. If the bottle cap is lying 45 degrees, the trace will appear elongated. The detector is seeing the flat surface shape and the narrow size of the object, which tends to show up on the upper ferrous limits. If you tilt the bottle cap on edge, the detector sees little of the flat surface, therefore appearing in the upper ferrous limits. EMI, electromagnetic interference, can also leave target trace. It appears around 0 to 2 and can be accompanied by a scattered trace. Now we're going to take a look at ferrous large and complex shaped targets. They can often create unusual shape trace and vary with orientation. An example is a bolt. It had a cylindrical shape, and the bolt head is giving highly conductive properties. In some orientations, it can cause the trace to slant down and to the right of the upper ferrous region into the non-ferrous region. Sweeping the target from different directions while checking the target trace can provide a better indication of its ferrous properties. A thick rusted iron bolt falsifying in one orientation. The same bolt checked from a different angle. Now we're going to take a look at a low conductive or a weaker target that is being masked or dominated by a close target. These will also create a unique target trace. As an example, a low conductor coin next to a stronger, more dominating iron signal. You will notice how the stronger signal will draw up the weaker signal, but detect a non-ferrous response as well. A low conductor coin on its own, a nail on its own, a low conductor being masked by a nail and being drawn up into the ferrous. I just want to show some detail. There is some difference between a masked low conductor trace to, let's say, a thick iron square nail with a large head, or a bottle cap at a 45-degree angle. This is why at the beginning I mentioned it is worth learning. Last, let's take a look at a low conductor coin buried deep in mineralized ground. Mineralized ground creates a challenge for discrimination, as the detector sees the target as a mixture of signals from the target and the ground response. This can cause a trace in the upper ferrous limits, on the center line, and in the lower ferrous limits. They can sometimes connect by a vertical line. I hope you enjoyed this tutorial, everyone, on the ID map and target trace. There's going to be more to come, so stay tuned.